Good morning, everyone. I'm going to try something a little bit different today. And if I am successful, I'm going to get all of you to thinking very carefully about the content of this presentation. We are fighting against this virus, and there are a number of things that we have to understand in order to be better able to fight this virus. There's at least two ways to understand the origin of this pandemic. It could be natural origin, it could be laboratory made, or it could be both. And the truth that we're seeking, unfortunately, in the world that we live today, is confounded by all of these factors, including, I'll just read some: misinformation, lack of data, issues of national security, cover-ups, and at the bottom, the one that's used the most, I know, but I would have to kill you if I told you. So let's look at a little bit of history. I came to San Diego and to join IDEC Pharmaceuticals in 1992. This was a small biotechnology company. And I won't go into all of the detail, but suffice it to say that there was a scientist there, this person right here, Dr. Mitchell Reff, who was an expert at molecular engineering. That's what it was called at that time. Today we call it genetic engineering. And he produced a vector, an agent that acts as a carrier, as a virus, that conveys genetically engineered DNA or RNA segment into a host. He engineered and produced that vector for the work that we were performing. So he created this RNA vector. We infected mammalian cells with that RNA vector. The RNA became part of the mammalian cell's genetic material. We cultured those mammalian cells in very large culture flasks, and we produced Ritoxan. And as you have heard me speak about Ritoxan in the past, I won't go into details, but suffice it to say that we grew it in very large quantities so that we could carry out clinical trials in lymphoma patients. And this is Ritoxan in the packaging as sold to patients. And this was the first monoclonal antibody approved for the treatment of lymphoma and has been the #1 product for the treatment of cancer worldwide. And I need to correct this slide because it's not up to 2013. It has been #1 up till 2019. And of course, we don't have the data yet for 2020. So the #1 product for the treatment of cancer, and that is important because it has turned out to be curative for some types of lymphomas. And in fact, over 50,000 lymphoma patients are cured each and every year. And that, thanks to good old-fashioned genetic engineering, and I'm talking about 1992. So because of that experience, I can tell you without doubt, and this is fact, that a virus can be produced through genetic engineering. It can be done in the lab, it has been done before, and it continues to be done today. Yes, I have done that. So we were engineering viruses more than 25 years ago. And then we got CRISPR in 2012. And it has been considered to be the top scientific discovery of the decade. And hold your breaths and pronounce this with me. clustered, regularly interspaced, short palindromic repeats. That's what CRISPR stands for. Time magazine has an excellent article dating back to 4 years ago on how CRISPR DNA editing works. Basically, there is a CRISPR molecule that's obtained from certain bacteria and other cells. And it carries a target sequence that you build into it, that you engineer into that molecule. And that molecule has these little scissors, and I'll show you how it works, and this little zipper-like part, and of course, the target sequence. This is the sequence that the molecule uses to identify a certain segment of the DNA that you want to change, that you want to engineer into something else. So that little molecule navigates around and investigates all of the long DNA segments until it finds one that's identical, green, green, red, red, yellow, yellow, blue, blue, to the target segment. And then it uses its zipper to unzip the DNA, opens it up into two strands. As you know, the DNA is double-stranded, as opposed to the RNA, which is single-stranded. Again, still matching, so it's holding on tight to what it's supposed to target. And then it uses its scissors to cut the DNA in front and in back. So it takes out that piece of DNA, and then the body can repair itself and bring in some other pieces to fill in that spot. So the body has sort of a proofreading capacity. Or the scientists can patch it. And how can they patch it? Well, the same molecule, in addition to the target sequence, may bring in a repair sequence and insert it into that hole that it created in the DNA. So it inserts, and this is a different sequence, entirely different sequence, one that you engineered to create and have that molecule, put it in place there. And voila, here you have the DNA re-engineered with a new sequence in that specific place that you wanted to insert it. This, my friends, is CRISPR. And it has been so important. Time had this issue where it called it the gene machine and the use of CRISPR, what CRISPR experiments mean for humanity. There are at least two ways to utilize CRISPR: for the good of mankind or for bioterrorism. Now, for the good of mankind, this is the way that it was intended to be used. CRISPR was intended to be used for the good of mankind. Make no mistake of that. And in fact, as a result of CRISPR, there are therapies that turn off tumor cell genes, making them easier to destroy by the immune system. New treatments for cancer. You can correct genetic defects of different kinds. In this case, I'm giving you as an example the genetic defect in Duchenne muscular dystrophy. But it can correct genetic defects in a number of other congenital illnesses. CRISPR can be used to deactivate genes in pigs so that organs grown in pigs like heart valves, liver tissue, and so on will not be rejected by the pig, will grow and can be harvested and transplanted into people. So you can receive something that was grown in a pig, but that will work in you and save you. In malaria, for example, it's used to edit in sterilizing changes so that the mosquitoes, the female mosquitoes, cannot reproduce and malaria will cease to be transmitted. In bacteria, use CRISPR to rev up the plastic degrading gene and turn bacteria into garbage eating machines. In wheat and in other edibles, you can edit out genes that make wheat susceptible to mildew. potentially leading to hardier crops. So a number of uses for the good of mankind that CRISPR can be put to. However, people will deviate from the good purposes that CRISPR was intended for and use it for other purposes that are not as good. And this statement dates back to 2016. CRISPR microbes driving infectious diseases are just a few DNA edits away from becoming super strains that could wipe out unprepared populations. I know that you can read faster than I can speak, but I wanted to have you see this letter and see this statement on the slide because it's so important. Just a few edits away from becoming super strains that could wipe out unprepared populations. Does that sound familiar? And in fact, shortly after 2012, James Clapper, who was then Director of National Intelligence, classified CRISPR as a weapon of mass destruction. And it remains classified as a weapon of mass destruction. This is how some people in humanity, a minority, but they're there, can turn something that was meant for the good of mankind into a weapon of mass destruction. CRISPR is very simple, and it is that simplicity that makes CRISPR so powerful and that raises the possibility that terrorists or rogue states could deploy it as a weapon. This is a reference from Time Magazine 2012. So 8 years ago, this was already being raised. Today, you can go online and order your own CRISPR kit for as little as $130. As $130, you can do CRISPR at home. Well, that's taking a little bit too far, but you can do CRISPR in a laboratory. The technique is being used in hundreds of laboratories across the US and around the world. In fact, the Chinese were one of the first to use CRISPR. So we are fighting this war, and it is a war. CRISPR has an important part to play in it, and I hope that today I've helped to illustrate the part that CRISPR may or may not have played. You have heard me, you have seen this presentation. You are, of course, free to make up your own decisions how you interpret this. Thank you very much for your attention.